Hey guys, welcome back to chapter 11. We are now going to get into the heart of this chapter, kind of everything leading up into this point, talking about something called colligative properties. So in the lab, this will be the lab that we perform this week, and they're actually really fun to kind of explore and get to know. So I'm first going to propose a series of questions, and by the end of this chapter, from here to the end, we'll be able to answer all of these questions. So if you ever wondered why we throw salt down on the sidewalks in the winter, so temperature is forecasted to get below freezing, and you'll see a bunch of businesses throwing salt kind of out in front of their doors. Or the other question is, well, why can some businesses get away with throwing salt down on the ground? Other businesses or people put sand down and it serves the same purpose. Why would that be? I don't know. Ever thought about the purpose of antifreeze? So we pour antifreeze into our engines and our vehicles. Antifreeze actually kind of serves a dual purpose. It's anti-freezing. So it prevents our engine blocks from freezing. It also prevents them from overheating. But how and why does it serve that purpose? And how does it serve that dual purpose kind of all in one? And then lastly, you are stranded on a desert island. You are surrounded by seawater, and yet you are at risk of dying from thirst, right? Water deprivation. So why can't you just drink the seawater to survive? Why do you have to have fresh water? All of these questions can be answered through the study of colligative properties. That's what we're going to do now. So colligative properties are going to be values that depend only on the number of solute particles that are dissolved in solution, not necessarily what those solute particles are. Okay? So up until this point, we've been talking all about solutions in chapter 11. So we're going to continue with that. We're going to be talking about solutions. And now we are no longer concerned with what particle is dissolved in solution. Now we're going to be more concerned with how many particles are dissolved in solution. And we're going to look at a series of properties that are affected by the number of particles in solution. So the colligative properties that we're going to study are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. In this video, we're going to go ahead and dive into vapor pressure lowering. The next video will be boiling point and freezing point. That'll be what we do in the lab. And then the last couple of videos will be on osmotic pressure. So let's dive into our first colligative property. Let's look at how vapor pressure is lowered based on the number of particles in solution. Well, first, let's talk about what vapor pressure was. So just as a reminder, so vapor pressure is the pressure exerted by a vapor in a closed system. Remember that this is a pure sample of water, so we haven't put anything in it yet. But remember, when we have a liquid down here, that liquid is intermolecular forcing with itself, and then some of those particles are going to start to evaporate, right? Vaporization. So liquid becomes gas, liquid becomes gas, liquid becomes gas. And then at some point, there's going to be a collection of gas above this liquid, and the collection of gas above this liquid is going to exert a pressure. That's vapor pressure. And then also, remember, we are at equilibrium here. So the rate of vaporization is going to be equal to the rate of condensation. So we're going to have kind of a constant vapor pressure above this. So let's think about, again, what particles are present for vaporization. So this is our pure substance here. And we mentioned in the last chapter that only the particles that are at the surface have an opportunity to vaporize, right? So it's only these particles at the top. So what happens when this is no longer a pure sample of water? What happens when we dissolve some sort of solute into that solution? All right, so we're going to add non-volatile solute. So let me talk about what this word means. Non-volatile solute. That just means that whatever solute I'm adding to the system is not going to vaporize, right? So we don't have to consider the vaporization of this solute. It's going to stay dissolved in solution. It's never going to become a vapor, okay? So the addition of a non-volatile solute, so mixing something in there, it's not a pure substance, will reduce the rate of vaporization, decreasing that amount of vapor. So when we put this non-volatile solute into our pure substance, so now we put salt in our water, what happens is those sodium chloride particles are now going to be competing for space at the surface. So instead of having, 20 water molecules that are available to vaporize, now the sodium chloride has taken 4 of those spaces. So now only 16 water molecules have the opportunity to become a vapor. So that's going to, of course, reduce that vaporization rate. That's going to reduce the number of particles that do vaporize. And if we decrease the number of vapor particles, that's going to decrease the vapor pressure. Now, there will be an equilibrium that gets reestablished, right? So immediately I put that solute in, and it's going to kind of halt or change that, like, one vaporizes, one condenses, one vaporizes, one condenses. It's going to kind of shake things up a little bit. But eventually we will reestablish equilibrium. We'll have the rate of vaporization equals the rate of condensation. But once we reestablish the equilibrium, it's going to be at a lower vapor pressure. There's going to be less particles that are a vapor. So when we would measure that vapor pressure, we would register a lower vapor pressure. Okay. So the cool thing about these colligative properties is the name of them kind of gives away what's going on. So this colligative property was called vapor pressure lowering. So it's going to lower the vapor pressure. Now we want to quantify this, right? I've given you kind of the qualitative explanation as to what's going on. Let's quantify this. How do we put this into math and prove this to ourselves with numbers? Kind of a busy our way through it. So Raoults Law is going to be the law that we use to calculate this change in vapor pressure. So Raoults Law says the partial pressure exerted by any component of an ideal solution is equal to the vapor pressure of the pure times mole fraction. Let me break that down. So what Raoults Law says is the pressure of the solution, so that vapor pressure exerted by the solution, is going to be equal to taking the vapor pressure of a pure solvent. So what is the vapor pressure of water before I add anything to it, for example? So taking the vapor pressure of the pure solvent and multiplying that by something called mole fraction. Okay. Vapor pressure of the solvent, this kind of degree symbol means we're using that standard that's given. So the vapor pressure for a solvent is always something that's going to be given. That's a standard. Those are well-known values, very much experimented, determined, and put into a table. So that's going to be the value that's given. Most of the time, the pressure of the solution is going to be what we're solving for. So the only piece that we need to kind of get to know is this mole fraction. What does mole fraction stand for? So the mole fraction The mole fraction is going to be defined as follows. So mole fraction is denoted with an X. On the bottom is going to be the total number of moles. And then on the top is going to be the moles of solvent. So mole fraction is just kind of, you can think of it kind of like a percentage, like what percentage of the particles are at the surface available to vaporize, right? So if this was a pure substance, the moles of solvent and total moles would be even. So this would just be a 1 value, right? But now we're adding particles to the solution. So now the number of particles that are available at the surface is less than 1, right? It's less than the maximum amount. So on the top, we're going to put moles of solvent. That's kind of what we're looking at here, right? We're interested in the solvent. How did that change? So moles of solvent on the bottom. Or on the top. When I say total number of moles, what I'm referring to here is moles of solvent plus moles of solute. So every single particle that's present in that solution, we're going to add up the number of moles for each of those. So this is probably the most quote-unquote difficult part of the whole equation. Is just making sure that we correctly calculate the mole fraction. So let's just take a look at an example together. So suppose we have a water sample at 25 degrees Celsius. There's 0.9 moles of water, 0.5 moles of a non-volatile solute. Pure water vapor pressure is 23.8 torr. What would the vapor pressure of the whole solution be? So my formula is here. I want to just kind of take inventory to the side. So pressure of the solution, fraction of the solvent, and then the standard pressure of the solvent. So let's read back through here. Suppose we have a sample at 25 degrees Celsius. That's just kind of telling us we're at like standard temperature. It contains 0.9 moles of water, 0.5 moles of a non-volatile solute. So again, that word non-volatile is just telling us it's not going to vaporize, but that's the solute that we add. So let's go ahead and use that information to determine the mole fraction. So remember, this is moles of solvent, and this is total number of moles. All right, so total number of moles, we've got 0.9 moles of water, 0.5 moles of our solute. So 0.9 plus 0.5, so 1.4 total moles. All right, on the top, we want our moles of solvent. Solvent is whatever is in greatest proportion. So we pick the bigger number between these two. Also, another good indication is water is very likely going to be the solvent. So we're going to put the 0.9 on the top. So we're picking 0.9 because that's our number of moles of solvent. So plug that into my calculator. I have 0.9 divided by 1.4. And I get a value for my mole fraction that is 0.64. Yep. The mole fraction is a unitless number. I know that because I've got unit of mole on top, unit of mole on the bottom. Those cancel, so that's going to result in a unitless number. So let's continue reading in our problem. Non-volatile solute, done. The pure water vapor pressure is 23.8 torr. So that's telling us when this was a pure substance, the vapor pressure was 23.8 torr. So that's telling us what that standard pressure is for the solvent. And then we are solving for the pressure of solution. Okay. So now we've got 2 out of our 3 variables. Now we just need to plug and chug to solve this. So the pressure of our solution is going to be our mole fraction, 0.64, times the pressure of our solvent, so 23.8 torr. So looking at our units here, whatever unit we put in is going to be the unit that gets spit out. So I'm going to take 0.64 times 23.8, and the new vapor pressure of this solution is 15.2. There we go, 0.2 torr. So we have kind of an indication in the name. We can ask ourselves, does this make sense? So vapor pressure lowering, we would expect the vapor pressure of a solution to be lower, and that is in fact the case. It does go down. Another thing to kind of keep an eye on to just check yourself is this mole fraction is always going to be a number that's less than 1. So multiplying by a decimal or a number that's less than 1 will also always cause this number to go down. So just some kind of tips and tricks to make sure you're really understanding the material. That is your introduction to Raoults Law. I'll have another video of an example, and then we'll move on to our other colligative properties. I hope you guys found this helpful.